Okay.
Thanks everyone for being here on a Saturday. So what I want to do today is give like a brief introduction to Bridgeland stability and how it connects to the birational geometry of the Hilbert scheme of points on P2 that we've been talking about, and like how it allows you to go further for other surfaces and things like that. So before maybe I start, so you see, when you talk about the birational geometry of moduli space, so birational geometry of a moduli space, there are various points of view that you can take to construct other birational models. I mean, I'm not trying to motivate here like why you might want to study the birational geometry of a moduli space, but you know, some examples of these kinds of things is that sometimes one compactification can be more useful for studying problems. Like if you're trying to figure out the topology of the moduli space, say you want to compute the Betti numbers, or say you want to solve some enumerative problems, sometimes having different birational models, you know, can be very useful if you want, like, depending on your problem. So, you know, the kind of question that you can ask, given the moduli space, how do you construct different birational models of this? And there are various approaches to this. So the first thing is that you can do the minimal model program. Let me write it as MMP. And, you know, this one doesn't particularly care that you are working on a moduli space, right? It's just given any variety, then you can run the minimal model program to get various different birational models, right? The other thing that you can do is that if you have a moduli functor, you could vary the moduli functor. Vary the moduli functor. Now, what does that mean? Like, say, for instance, you're thinking about, you know, moduli spaces of stable curves or something like this. And, you know, the Deligne-Mumford moduli space tells you that you should only put nodal curves, you know, satisfying certain properties as your degenerations. But then you could change that. Maybe you don't want to just allow nodes, you want to allow cusps and things like that. So you can sort of change the objects that you're parameterizing. Or if you're talking about the moduli space of sheaves on the surface, you know, remember that stability depended on an ample. So what you could do is you could vary the ample and things like this. So you could vary the objects that you are parameterizing and try to get slightly different moduli spaces. And then a third thing that you can do is, in case the moduli space is constructed via GIT, what you could do is you could vary GIT. So variation geometric invariant theory. And, you know, these kinds of, this sort of different ways of approaching the moduli space can give you different models, and depending on your problem, you might get simpler spaces. So, you know, initially when we started thinking about this now, almost a decade ago, the question was, how do you vary the moduli functor when you're thinking about the Hilbert scheme? So like, you know, let me remind you, we have this X smooth projective surface, and Xn is the Hilbert scheme of n points on X, right? It seems like there isn't all that much you can vary because, like, you know, the invariants here are discrete. You know, it's not like you can vary this n, then you get totally different spaces. So what is it that you can do? And then the idea goes back to, you know, Bridgeland and, you know, Bertram and, you know, many other people here. But the main idea is maybe you can vary the category. So the way you should think about this is that, this is a moduli space of ideal sheaves of length n, right? Maybe instead of, well, one thing that we could vary is the underlying category, the category of sheaves, okay? And so there was, Bridgeland introduced this idea. So maybe let me introduce it. So this is Bridgeland stability conditions. Again, I'm not going to do all the, details or like, complete definitions in here. I'll just highlight some properties and some things that come into play. But, the way I want to motivate this was, as a way of sort of constructing birational models, as a way of varying the functor. And then the underlying idea is the one thing that you can still vary is the category. So now what is a Bridgeland stability condition? It's a pair for us, A and Z. So it's a pair satisfying some conditions. Now, what is this pair? So first, A is an abelian category. And the technical condition, is it's the heart of a bounded T structure. Heart of bounded T structure in the derived category of sheaves on X. Bounded derived category of sheaves on X. And you don't have to worry too much about this. If you don't know what this means, it doesn't matter. Think of it as a reasonable abelian category that somehow generates this bounded derived category, okay? And now what is Z? Z is a group homomorphism. So this is a group homomorphism from the K group of A to the complex numbers. So it's a pair of things. It's an abelian category together with a group homomorphism from the K group of A to the complex numbers. And then of course it has to satisfy some properties. So now what are some of the properties? And here the way you should think about is we need to build a theory for which stability makes sense. Stability makes sense, right? And the way you should think about it is that this Z is going to take the place of things, kinds of stability things that we talked about, like the reduced Hilbert polynomial or the slope, right? So Z will sort of replace things like the reduced Hilbert polynomial or the slope, okay? So now what are the conditions? So satisfying, so it's a pair, I have an abelian category together with a group homomorphism satisfying a bunch of conditions. The first condition is that if you have a non-zero object in this A, right, then I want Z, sorry, what I just, if I have a non-zero object in this A, then I want this Z of E to be in the upper half plane. So what does it mean to be in the upper half plane? It just means that you are allowed to be in the negative reals. You're not allowed to be zero or the positive reals in the imaginary axis. The imaginary part has to be positive. So in other words, I can write this thing as REI theta such that R is always positive and theta is between 0 and pi. I allow pi, but I don't allow 0. Okay, in this upper half plane. So now the reason why you do this, now I can talk about now the slope of an object, right? So I can talk about the Z slope of an object, non-zero object, and let's see. So it is minus, I think, the real part of Z divided by the imaginary part of Z. Okay. With the understanding that, if the imaginary part is 0, then this is defined as plus infinity. Okay. And you need something like this to be able to make sense of this, yeah? Okay, so then you see what So as I said, this is going to give us a way of measuring slope, and this is a way that you can measure slope. So once I have this, of course, now I can talk about the semi-stability of objects in this abelian category, right? With respect, maybe we call this Brislan stability condition sigma. Maybe instead of mu of z, I should call it mu of sigma, but you know, mu of sigma. Right now, I can make sense of what it means to be semi-stable in this A. So you call an object E in A sigma semi-stable if for all sub-objects F, and I can talk about sub-objects because this is an abelian category, right? You have that the slope, the sigma slope of F is less than or equal to the sigma slope of E. Okay? So this function, this group homomorphism, allows us to talk about, like, sort of, you should think of it as playing the role of slope function or the reduced Hilbert polynomial in this case, okay? All right. So that's the first condition. The second condition was that, you know, we had a harder Narasimhan filtration when we talked about stability. That meant that given any bundle, you could filter it such that the successive quotients are semi-stable objects, and you require the same thing here. So you ask that every object E in A, right, has a filtration. So, you know, you have E not equal to 0, a finite filtration after some number of steps, right? It stops, and you want that the successive quotients to be semi-stable. I guess I want that to be I. You want this thing to be sigma semi-stable, and you want that the slopes are decreasing. Okay, so in other words, this is called the harder Narasimhan property, or typically H-N property. So you want that the pair satisfies the H-N property, and then there is one other property that you impose, which is called the support property, which I'm not going to even tell you what it does, but the basic idea that you should get out of this is that the Brislan stability condition is a pair of an abelian subcategory of your derived category together with a group homomorphism like this, satisfying some positivity property so that you can define slope. And then you want the slope to have, you know, some of the usual properties like harder Narasimhan filtrations and things like this that you love from ordinary stability. Okay, so now what I should do is I should give you one example and one non-example, and then the main example. Okay, so let's do an example. So if X is a curve, so Riemann surface, right? Smooth curve, smooth projective curve, right? Then what you can do is you can take your A just to be the category of coherent sheaves on X, right? That's a perfectly nice abelian subcategory of the derived category of coherent sheaves on X. And then you take your Z to be minus the degree plus I times the rank, right? So now you see, if I look at the slope here, right? This mu Z, or let's call this thing sigma A comma Z, right? Then this mu sigma is the usual Mumford slope, degree over the rank. It's the usual slope. Okay, and it's easy to see that, you know, it satisfies these kinds of properties. So, like, you know, if you have a coherent sheaf, right, its rank is positive unless it's torsion, right? So you know, if you have a coherent sheaf on the curve, so this is coherent sheaf, then the rank of F is always greater than or equal to 0. And if the rank of F is equal to 0, then it's torsion, so it's the degree of F then is positive. So that you see that you know, this function satisfies the positivity. Unless the sheaf is 0, then of course the degree is 0. But if the sheaf is non-zero, then the degree, if you have a rank 0 sheaf, then the degree is positive. So you see that the C is positive, and the Harder-Narasimhan property is the usual Harder-Narasimhan filtration for coherent sheaves. Okay? So that you see that you get an example, which is the familiar example in the case of a curve. Okay? Now let's do a non-example. You would think that if I have a surface now, I could do the same thing, right? I mean, if you have a surface, I still take the category of coherent sheaves. After all, that's what I'm interested in, right? And then, you know, you could do the same thing, like Z, you could take the degree mi plus I times the rank. I mean, so like the way we should do this, maybe, let me maybe write it like this. So Z of E, you can take it to be minus C1 of E dot H, say that you have some ample plus, you know, I times the rank of E or something like this. All right. The point is that this is non-example. Why is it a non-example? It's because it does not satisfy positivity. I mean, it is still good that, you know, if you have any coherent sheaf, you know, then its rank is non-negative, right? But the problem is that if the rank is 0, if you have a torsion sheaf and the torsion sheaf is supported on the curve, of course, this is a positive number, right? So then it's okay. I put a minus sign so that we land in the negative real axis. The problem is for torsion sheaves supported on points. If E is, you know, a skyscraper sheaf supported on the point, if E is skyscraper supported at one point, say P and X, then you see that this Z of E is 0, even though, you know, E itself is not 0. So it doesn't satisfy this positivity property. Okay? In fact, it turns out that you cannot make an example of a Brislan stability condition on the surface if your heart is the usual coherent sheaves. You need to do something. Okay? All right, so what do you do? So let me give you the main example. And all I care about for the purposes of this talk is that these are examples. So the main example. And these are due to Bridgeland and Arcara-Bertram. Maybe I should put some names here. Bertram. And, you know, with contributions from many people like Toda, Macri, and Byron Macri, and, you know, like the theory, like the sort of the problem of constructing stability conditions on varieties is very active, especially on threefolds. But, you know, the original beginning examples on surfaces are due to Bridgeland and Arcara-Bertram, and with some contributions with people like Toda and, you know, Bayer, Macri, many people. So, okay. So what do? The idea is this. So we have this problem that, you know, the category that we would really like to work with doesn't support a Bridgeland stability condition. So the idea is that you do something called tilting. Okay, so let me tell you what that is, and it's like this. Say that you have a torsion pair. So now what's a torsion pair? So that we have T and F. So A is an abelian category. So this thing is a torsion pair. Now, what does it mean? It means this is two subcategories of A. Okay, and the thing that you should remember, T is of course for torsion, F is for torsion free. And then, it should satisfy the axioms that, a torsion sheaf and a torsion-free sheaf should have, right? So now what are those? So the first thing is that there should be no homomorphisms like hom from T to F should be 0 if T is in this T category and F is in this F category. And the way you remember this is that if you have a torsion sheaf and a torsion-free sheaf, you don't have any homomorphisms from the torsion sheaf to the torsion-free sheaf other than 0, right? And the second thing that you want is that any object in A should be written like this, where this is in A, this is in T, and this is in F, right? Again, the way you remember this axiom is, again, think about the sheaves. Every sheaf has its torsion part, so, and the quotient is torsion free, okay? Okay. Okay, so these are the axioms. And then if you have such a torsion pair, what you can do is you can tilt this category. So now what does it mean to tilt this category? So you tilt the category with respect to this torsion pair. So maybe, I think you just denote it like this or something like this. Maybe I remember that this with respect to this torsion pair. And what it just means is that you look at complexes, okay, such that, the minus first cohomology of this complex lies in F, and then the zeroth cohomology of this complex lies in T, and then all other cohomology is 0. Okay, so then you get a new category in the derived category. It turns out that this is also an abelian category, and if A was the heart of a bounded T structure, so is this one. Okay, so this allows you to get the new abelian category. All right. Okay, so now, so just maybe let me write this new bounded heart of bounded T structure. Okay, so now this is what we are going to do to our category of sheaves, okay? So what we are going to do is we are going to tilt it with respect to a torsion pair. So let's do it. So this is our main example of, so here is what I'm going to do. So I'll have TS and FS. So let's see whether I can do this. So this is going to be all sheaves, okay? Such that the slope of so I'll fix an ample. So remember, I have my surface X, H is some ample, right? So what I'm going to do is like this. So I'm going to look at sheaves such that the H slope of G is greater than S times H squared, okay, for all surjections E onto G. Like if you get the surjection from E to G, then the H slope should be bigger than this SH squared. And then F will be, a similar thing, right? So this mu H of F, say, is going to be less than or equal to SH squared for all now injections into E. Okay, so the way you should think about it is that you look at sheaves E such that in the Harder-Narasimhan filtration, with respect to the Mumford slope, all slopes are at least SH squared, bigger than SH squared, and you look at those where all slopes are less than or equal to SH squared. Okay, this is a torsion pair, right? So this is a torsion pair for, you know, the category of coherent sheaves, right? And now, why is it a torsion pair? Like, you know, if you have something with slope bigger than sh square, right, where all the Harder-Nursemhan factors are bigger than sh square, then you can't map to something where all the Harder-Nursemhan factors are less than or equal to sh square, right? By stability, by slope stability, then any map like that has to be 0. And if you have any sheaf, then you can split it into parts where the Harder-Nursemhan factors have slope bigger than sh square and those that have slope less than sh square. Okay? So it is a torsion pair, and then what you do is you tilt. The category AS that we are going to take is the tilt of the category of coherent sheaves with respect to this pair. Okay? All right, so that's the category that we are going to take. And again, I mean, you know, how can you, like, I mean, this might seem like a really scary thing, right? But for a first approximation, what you can think of is like this. It wasn't enough to just consider one sheaf to capture the kind of geometry that we are going to think about. So instead, what you need to do is you need to consider pairs of sheaves with a morphism between them. I mean, this is not completely correct, right? Well, I really don't want that to happen. Okay, sorry about that. You know, this is not entirely correct, right? Because, I mean, you're really looking at complexes, but, you know, to a first approximation, you can think of what's happening here is that you consider, you know, instead of just one sheaf, you know, two sheaves together with a map between them where the sheaves are, you know, the domain is in FS and the target is in TS. Okay, to a first approximation, you can think of it like this. And so it's not that scary. It's just instead of one sheaf, you have two sheaves with a morphism between them. So it turns out that that's enough to capture a lot of the complications in geometry that we want to study. Okay, and then I need to also tell you what the Z is. So this Z will depend on two parameters. So this S is the same as that S, and then I'll have, so, and I want this to be minus the integral over X, so e to the minus S plus ITH times the ch. So, you know, it's going to be like this. All right. And then the theorem here is, I mean, originally due to Brisland for K3 surfaces and extended, you know, by Arcara and Bertram, is that this pair is a Brisland stability condition. And what I do need to say is that this T is a positive real number here. S is an arbitrary real number, but T is a positive real number. Okay. I would normally maybe babble a little bit why this is a Brisland stability condition and how it fixes this problem we had with torsion sheaf supported at the point. But I think I'm going to skip doing this. I'll just say that, and I didn't attribute. This is Bridgeland and Arcara Bertram. Okay. Okay. So I think that I'll just say that this is a Brisland stability condition. In particular, you see what this does, right? I mean, once I fix my ample H, then I get a half plane of stability conditions, right? Let me write S, here is my S, and here is my T. You see, you get a half plane of stability conditions. And this, of course, depending on this H, like as you vary the ample, of course, you get more. But this sort of reflects, you know, one of the main theorems of Bridgeland. So the theorem of Bridgeland is that, so maybe I should just mention it. Bridgeland is that, you know, the space of stability conditions on the projective variety X is a complex manifold. And this is the set of stability conditions on smooth projective variety X. Okay, so you see that, you know, here you see one slice of this complex manifold constructed in this particular way, this upper half plane. Okay. So now what's nice about this is that there is a there is a wall and chamber decomposition. All right, what does this mean? Here is what you do. What you do, fix a Chern character. V. And then what you could do is, you know, I'll just work on this half plane of stability conditions because for P2 this is going to be enough. But you know, you could talk about this wall and chamber decomposition in this complex manifold. But I'll just, like, you know, restrict myself to these examples that I've shown you right now. What you could do if you fix a Chern character, then what happens here is, so let me Chern character, say this is V of E, here is the slope of E. Okay, what happens is that there are chambers. So, sorry, there's a question. Is this a complex slice in the moduli space of, yes, it is a complex slice. All right, so there is a wall and chamber decomposition, and let me draw it suggestively. Let me draw it suggestively like this. There is a wall and chamber decomposition. And the way you should think about it is, what is this? What it is that you see, so I have my category A, and I can ask when, and I can look for each sigma, right? Here it depends on these S and T, right? I guess this, the category depends on S, the function depends on S and T, right? In each object, I can ask, what are the sigma ST semi-stable objects in AS, okay? And then you see, if you stay within a chamber, then the set of semi-stable objects is not going to change. And occasionally you will hit a wall where, you know, some objects get destabilized and potentially some objects become stable, so there is a change. And then you go to another chamber, and then in that other chamber, then again, the semi-stable objects stay the same, okay? So a chamber, in a chamber, the sigma semi-stable objects in AS remain the same, okay? Now you see, you can figure out what, at least what the shape of these walls have to be, and, you know, they are either a vertical line at mu E or semicircles, nested semicircles like this in this half plane. And, you know, this is not mysterious. You know, what you need to do is you have the formula for it, right? so, I mean, to say that, okay, to say that you have E, right? To say that this thing becomes semi-stable at some point and for some stability condition means that there is some object F, right? Sub-object F, and initially when you are in some chamber, this U sigma of F is less than this. Maybe let's do it like this: U sigma ST. Maybe let's say S naught T naught, S naught T naught of E. And so here is the picture. say that you are in some S naught T naught, and then, you know, you have an object, sub-object, because this thing is stable, then the slope has to be less, right? But as you change the stability condition, you vary this function, right? What can happen is that at some point, these slopes, you know, this was S naught T naught, here as maybe S1 T1, it can happen that this mu sigma S1 T1 of F becomes equal to this mu sigma S1 T1 of E, right? And when that happens, then that object is no longer stable, but it becomes semi-stable, right? And, you know, typically what happens is that when you cross, then actually the inequality reverses and you become unstable, right? Okay, so then, you know, what you need to do is, in order to find walls where these kinds of things happen, and I don't know, where these kinds of things happen, what you need to do is you need to equate mu sigma, you know, of F with mu sigma of E. And what you can do is you write down, you know, say that this has rank RCD, rank first Chern class, second Chern class, Chern characters. F has R prime, C prime, D prime, right? And you know the formula for this. It's not, you know, a mystery. I told you what the formula is. So you plug into the formula and then you complete the square so that you see that you get nested semicircles. And in fact, you can say exactly, you know, where the, I mean, you know, the center of the semicircle. If you really want the equation, I can tell you what the equation is. The center of the semicircle, you know, if the wall is given by objects F and E where, you know, the slope of F and E are equal, then the center is at S equals a half phi mu of F plus mu of E. I think then it's minus delta of F minus delta of E divided by mu of F minus mu of E, I think. So the center occurs at S comma 0, right? For this is the coordinate for the S. So like, you know, S of the center. So it occurs at S of the center comma 0. And you can work out the radius too. If I'm not mistaken, the radius square is something like S minus mu of E square minus 2 delta of E or something like this. Anyway, it doesn't matter what these things are precisely, and hopefully I'm not, you know, miscopying these things from my notes, but, you know, you can work this out. It's not hard, okay? All right, and the way you should think about this is that, you know, there are moduli spaces of sigma semi-stable objects in this category AS, and as long as you stay within the wall, your moduli space is staying constant, but now as you hit these walls, the moduli space is changing. All right? So what this means in some sense is that Bridgeland stability allows you to have a way of making sense of what I started with originally. So maybe let me go all the way to the beginning of the lecture, right? The way we started the lecture was, you know, we wanted to do the birational geometry. You know, one way was to do the minimal model program. Another way was to vary the moduli functor. If you start with something like the Hilbert scheme of points, it's not at all obvious what it means to vary the moduli functor. And, you know, the idea coming from Bridgeland and Aaron Bertram and company was that we could maybe vary the underlying category, and Bridgeland stability allows you to do that. And, you know, you get these other moduli spaces that are, you know, often birational to the one that you started. Okay. Maybe what I want to do next is, you know, this is so completely abstract so far, but, you know, it's actually fairly concrete. So what I want to do is maybe do a few examples so that we get our hands on it, you know. So let's do a few examples. And let's start simple, right? Let's take the case when we had 2 points and say that we have P2 of 2. Okay. So we understand the birational geometry of this thing fairly well. So let's just draw sort of the picture here. What we have here is we had our H, we had our B, and here we have H minus a half B, right? So let me remind you what these things were. So so I'm drawing for you the Néron severity space and various cones in there. So what were H and B? So remember, B is the divisor of non-reduced schemes. So this is when two of the points collide, right? And H is, you know, you fix a line on your P2 and you ask that one of your points lies on the line, okay? And what we've discovered before is that this is the ample cone. This is the ample cone. This is the effective cone. And in fact, we know, right, what these models are. So what are these models? We've discussed this before. I have one morphism from the Hilbert scheme, so P22, to the symmetric product, and H is the map that gives you this. And we've also seen what this map is, right? I have a map from P22 to P2 dual. Given by, you know, given 2 points, you send it to the line spanned by those 2 points. And this is a morphism even when you have a non-reduced scheme, right? You have a well-determined line, okay? And so this is given by H minus a half B. So that you see that all the interesting models that you can see from this picture, you get the Hilbert Schemes morphism and you get this map to P2 dual. Now the question that you can ask, okay, what are the possible walls? So how about in the Bridgeland world? What happens in the Bridgeland world? Well, here I have my ST plane. Oop, the ST plane, and I already, this is my T axis, this is my S axis, right? And then, you know, the kind of question you can ask, what is it that happens? And then it turns out, so there are some things that I didn't tell you that I should have told you, right? Here, there is basically only one wall. Whoop. Here, there's basically only one wall. This is a semicircle, despite all appearances. Okay, and the one wall is given by having a map from O of minus 1. Okay, the destabilizing object is O of minus 1. And so, you know, you ask, when do you have a map from O of minus 1 to IZ? Okay. And then what happens here is that, maybe let me change my color here. So you have the Hilbert scheme up here. Oops. The moduli space of Bridgeland stable objects, if you are in this region, is isomorphic to the Hilbert scheme of 2 points. And here you just have the empty set. Everything gets destabilized at that point, okay? Now you see, to see this, of course, every ideal sheaf of 2 points admits a map from O of minus 1, because if I want to write the resolution, right, the resolution looks like this, right? If you have 2 points, then they're always contained in a line, and it's cut out by a quadratic equation on that line. So it's always written like this. So you always have a map from O of minus 1 to IZ. And, you know, in this case, you know, once you have like all the ideal sheaves are destabilized by O of minus 1. Okay, so that's the picture, and as you can see, it's fairly similar to this picture. You had one wall here and one wall here. Okay, it turns out this is a general feature. This is a general feature. When we are talking about P2, there are only finitely many walls. When we are talking about P2, then there are only finitely many walls. In both pictures, both in the Bridgeland picture and the Mori picture, it turns out that, you know, moduli spaces of sheaves on P2 are Mori dream spaces, okay? So there are only finitely many walls, and in particular, there's always a largest wall.
So I have a question. What is the second sequence in black from?
The second sequence in black is the define the ideal sheaf of any 2 points, right? It always has a resolution like this, right? If you have 2 points.
Yeah.
Oh, sorry. Because it's wrong. I was doing 1 point. Thank you for catching that. What I meant was this. Thank you for catching that.
Right.
Okay. If you have 2 points, right, then, you know, it's always contained in a line, even if it's non-reduced, and then it's generated by a linear equation, a quadratic equation, and then the syzygy is, you know, happens in degree 3. But you always have a map from O of minus 1 to IZ. Thank you. The general feature, in P2, there are only finitely many walls, and there is always a largest wall. And when you're talking about the Hilbert scheme of points, right, then it turns out that the largest wall always is given by O of minus 1. Okay, so in other words, when I'm drawing this this picture, right? So here is my I seem to not be able to draw. Here is my S, here is my T, here is the origin. There is always a largest wall given by O of minus 1 mapping to IZ that destabilizes it. And that is always the largest wall. So, you know, what does that mean? So let's reinterpret what that means. Now, there's a question about how do you prove this? So maybe I'll describe a little bit how you prove this. But suppose that you knew that there was always, I mean, since I told you there are finitely many walls and they are all nested semicircles, right? So then there has to be a largest one. And I'm claiming that when you talk about the Hilbert scheme of points in P2, then the largest one is always given by O of minus 1. So let's interpret this in terms of our description of the ample cone, and then you'll see that it will match what we had before. And that was, you know, the question is, when do you have a map? When do you have a map from O of minus 1 to IZ? I claim that you have a non-zero map like this if and only if Z is collinear, right? Z, I mean, you have to give like a degree 1 polynomial, but this degree 1 polynomial has to vanish on Z to map to IZ, right? So that means that these points have to all be collinear. So what this is saying is that you know, the first time, so the way, okay, so I should have said one more thing in terms of the general features. If you're just talking even in general, and this is has nothing to do with P2, so you know, you have this largest wall. The basic fact is that as you fix S and you let T tend to infinity, then the moduli space becomes isomorphic to the moduli space of Giesecker semistable sheaves. So the Bridgeland moduli space as T tends to infinity, the Bridgeland moduli space becomes isomorphic to the Giesecker moduli space we were talking about. Okay. Right. So that, you know, if you make T very large, then you'll get the Giesecker moduli space, the moduli space that you're interested in. Again, I mean, how do you prove this? You need to go back to the equation and just really study, you know, what does it mean to be stable with respect to this, to some object when T is with respect to some stability condition when T is very large. And if you study what that means, is that basically you recover, you know, the conditions, the condition for the Giesecker semistability. But so the way you should always think about it is that, you know, you start with the moduli space that you're interested in, which is the Giesecker moduli space somewhere up here. And what you want to do is what transformations occur as you go down, as you bring T down. So that when T is large, then you have your moduli space, but occasionally as you cross some walls, then you get some birational or, you know, some transformations of this, moduli space. And then the game becomes understanding like which transformations occur, okay? And now let's see, so in terms of if we go back to the Hilbert scheme of points on P2, then I'm claiming that the largest wall is always given by O of -1, and that means that you have IZ and you have a map from O of -1 to IZ that's non-zero, right? That means that Z is collinear, and I claim that we've seen this before. So the way you should think about this is that, again, maybe let me draw it again. So we have this wall given by O of -1 mapping to IZ, right? If you think about it, so I have my moduli space here, which is the Giesecker moduli spaces, and I come down. The first time I make any changes is, you know, when the points are collinear. So the way you should think about this is that this largest wall is sometimes referred as the Giesecker wall. And you should think of it as corresponding to an edge of the ample cone. Okay. There is you can make this precise that it is indeed corresponds to the edge of the ample cone corresponding to that wall. There is a Neff divisor constructed by Bayer-McCree that sort of tells you that what is going to happen. But you see, the key point here is that we've already seen this. We've talked about what the ample cone of P2N is, right? And then we saw that, you know, this was spanned by age and n-1 age minus b/2, right? And, you know, in this Neff divisor, the locus that got contracted was precisely the locus of points that were collinear, right? So not surprisingly, the fact that the ample cone, so the edge of the ample cone corresponds to that wall, okay? Now, you see, we're not going to do this simply because we don't have time, but you know, you can reverse this process. You can reverse this process. And so we classically computed the ample cone of this thing, and now we are saying that, look, that corresponds to this being the largest wall in Bridgeland stability conditions. But you know, you can reverse this thing. You can instead study the largest wall in the Bridgeland picture, right? In the Bridgeland slice that we discussed, right? And then you can this way actually compute the ample cone. So people have done this for various surfaces, you know, some example, like, you know, this is a paper with 8 authors, and I can never get all the authors. But, you know, it's Jack Huizinga, Matthew Wolf, Eric Riedel, Barbara Bolognese, Xiao Lei Zhao, and what's his name? Okay, so I'm blanking on the name. I should have looked up the names. But so you know, for instance, they can compute the ample cone of, you know, Hilbert schemes of points on surfaces like in P3 and, you know, even more complicated surfaces. So, you know, you can reverse this to do this kind of calculation. All right, so these are some of the general features of this picture, but let's keep going. Let's do one more example, okay? So maybe the next example that I want to do is 3 points. Why not?
Can I ask a question about the largest wall?
Yeah.
So the locus of sheaves destabilized at that wall would be like a PN bundle over the P2 dual.
Yes.
Right. So when you cross that wall, is that flopped, or is that just contracted, or what's the general behavior?
I think you get the flip typically.
Okay.
Yeah, I mean, typically you get the flip.
So for n equals 2, it just
right. I mean,
that's a special case. Right?
N equals 2 is a very special case because that's a contraction. Like you go to that's just the contraction. But let's do maybe 3 points or 4 points.
So 3 would be a divisor, and you're saying
3 will be a divisor, but once you come to 4, then that will be higher codimension.
Right.
So let's maybe quickly do n equals 3 and then maybe n equals 7 or something like this so that you see what kinds of things happen. So at n equals 3, so we have here again H and B, right? And then here there are 2 things. First, there is 2H minus B over 2. And here there is H minus B over 2. So let me remind you what these things are. So let's maybe change the color. So here is my ample cone. Right? Here we always know that B is in the stable base locus. So H as usual gives the Hilbert Schemes morphism. And we know what this map is as well, right? So how do you get a map? So this 2H minus B over 2, remember, came from mapping P23 to polynomials of degree 2 vanishing on this thing. So this maps, if you want, to G36, right? The Grassmann, you know, 3-dimensional subspaces of a 6-dimensional vector space. And what it does is that it contracts the divisor of collinear points. So contracts the divisor of collinear points. And then, of course, in this here, this divisor is in the base locus. The divisor of collinear points is in the base locus. All right, so now let's just see what happens in the Bridgeland picture. So let's also draw the Bridgeland picture, and let me maybe open my notes before I make a mess. So then you see, let me maybe change So what happens in the Bridgeland picture? In the Bridgeland picture, there are, again, here is your S, here is your T. There are two walls in this case. This is, again, the wall given by O of -1 mapping to IZ. And then here is another one. And here actually two walls coincide, and you can view this in two different ways. Here, either O of -2 mapping to IZ, or IP of -1 mapping to IZ, right? And then you see what happens here is that, you know, you have the Hilbert scheme here. When you cross here, you've contracted the divisor, and then everything disappears once you hit here, because any 3 points, you always have a quadric conic containing 3 points, okay? And maybe more interestingly, let's also try doing n = 7 or something like this, so that you start getting a sense for what happens. All right, let me see whether I can actually reproduce this. So here is an H, here is my B. So then here there will be many, many things not drawn to scale. So let me see, 1, 2, 3, 4, 5, 6, I think is what I need. This is 6H minus B over 2. This is 5H minus B over 2. 4H minus B over 2. 3H minus B over 2. And here I have 5/2 H minus B over 2. And then finally 12/5. 12/5 H minus B over 2, I think. Okay, so now let me describe a little bit what these things what these rays correspond to. Again, we know that we have the ample cone here, right? This is the ample cone. And then these divisors correspond to, like, you know, giving maps to various Grassmannians, right? So we have a map from P27 to, to the Grassmannian of H0 of IZK, right? Mapping, like, the map is, okay, let's just this. We have the vector space of polynomials of degree k here of dimension k plus 2 choose 2. And here you have k plus 2 choose 2 minus 7-dimensional subspaces. And then, you can do this for k equals 5, 4, 3, 2, and so 5, 4, 3, 2, yeah? I mean, 6 gives you this one, so you can do maybe 6, 5, 4, 3, right? And then I have the pullback of O of 1, and these correspond to these various rays, right? Okay, so now let's describe what are the base loci in these various places. So you see, once you cross, so here you have the base locus is, Z such that are collinear. Here, you can ask, when do like 7 points fail to impose independent conditions, on polynomials of degree 4, this is if 6 of the points are collinear. So you have a subscheme of length 6 that's collinear. Not surprisingly, here you have 5 of the points collinear. So you have a Z prime and Z, the length of Z prime is 5 and Z prime is collinear, right? Yeah, then here what happens here is either 4 of the points are collinear, all 7 points lie in a conic. So here, you have 4 collinear points, or 7 points lie in a conic. And finally here, you have 6 of the points lie in a conic. And you can work these things out by knowing what these divisors are. The only interesting one is this one, and I haven't told you what that one is. But you can view that as a Brill-Noether divisor corresponding to, TP2 of 1, if you want. Like, sort of, there is a way of describing this in terms of what we were talking about last time. But the way you should think about it is that, at least the beginning walls are pretty easy to understand. And as the number increases and you go further and further deep towards the effective cone, then things get more and more complicated. But initially what you think happens, right? Like, first, the most special position for 7 points is that if they're all collinear. Then the next one is if 6 of them are collinear, then 5 of them are collinear. Then at some point, all of them lie in a conic. And then, as you go deeper and deeper, then you'll start seeing more and more higher rank vector bundles. Then you'll have things like, points that fail to impose independent conditions and sections of the tangent bundle or some other kinds of bundle, okay? So that's the picture that you get when n equals 7. And then there's a corresponding picture for Bridgeland stability. And let's see whether I can draw that one. So here I have 1, 2, 3, 4, 5, 6 walls again. 1, 2, 3, 4, 5, 6 walls, just like that one. 1, 2, 3, 4, 5, 6. As we said, this is O of -1 mapping to IZ, right? Here you get IP of -1 mapping to IZ. Here you get IPQ of -1 mapping to IZ. Here you have 2 walls colliding. It's O of -2 mapping to IZ, or there are 2 descriptions of this wall, or you have IZ prime of -1 mapping to IZ, and here the length of Z prime is 3 now. Here it's IP of -2 mapping to IZ, and then this final wall is given by TP2 of -4 mapping to IZ. Okay. All right, so the way you should think about this is that what happens here is, let me just maybe start. I did terrible paper. Let's maybe put a red one here. Say that you start here, so you have your Hilbert scheme, right? What happens here as you go down, right? You hit this wall corresponding to O of -1. Then you see, like, the sheaves, the ideal sheaves that were all lying on the point become destabilized. Now you see, just like you asked, NADA has much higher codimension, right? So what you do is you get some sort of flip, right? And now you have a new moduli space, and that new moduli space is, you can interpret it as a moduli space of Bridgeland's stable objects here, right? And you can describe the flipping, like you can describe the locus, like what you replace with in terms of the extensions. Basically, what's happening here is that, if you have this IZ and you have this O of -1, right? Then in this category, there's some co-kernel. Let me call it Q, right? And what you do is, once you're at the wall, then, the slopes of all of these things are equal. And what happens here is that when you pass the wall, then the slope of this guy becomes bigger than the slope of this one. And this, so now what you do is instead you need to look at extensions that, flip those 2 things. Okay, so what you do is basically you replace, IZ with extensions that are given the other way. Okay, And then you can keep going, like, you know, the moduli space constant for a while until you hit IZ, where that admit a map from IP of -1. Now, when do you admit a map from IP of -1? Well, you see, this map is given by a linear polynomial, right? So that what has to happen is that, you know, P is part of your scheme, but all the other points have to be collinear with the zero locus of that linear polynomial, right? So that this says what gets destabilized at that wall is schemes that have a subscheme of length 6 that is you know, collinear. And then you keep going, you flip that locus, you keep going, and then, you know, then you destabilize things that all but 2 of the points are collinear, then you go some more, and, you know, then you destabilize 2 loci, either those points that lie on a conic, or, you know, 4 of the points lie on a line, and so on and so forth. Okay, and finally, when you hit this TP2 of -4, right, what happens is that you know, all the schemes of length 7, their ideal sheaves admits a map from those so that you destabilize the whole modular space. Okay. So what you see already from these examples, I mean, I'm not telling you exactly how you say that these are the only walls, but, you know, very briefly, what would you do? You know, you can get inequalities. There are inequalities that tell you, like, you know, if you have a higher rank object. So you see, the one thing that you have to be careful in this brittle instability is that normally if I'm talking about a sheaf, right, you know, any subsheaf of this sheaf of rank 1 has rank 1 again. You know, you can't have a higher rank sheaf injecting into this IZ. But here you have to be careful, right? Because we're not working in the category of sheaves. We are working in this category, you know, in this slightly strange tilted category. So you could have that in this category that a higher rank sheaf injects into this IZ in AS. This is, of course, not an injection of sheaves. It's just an injection in this category AS, right? But you can bound the invariance of this from some of the data that we have here, right? There is a way of bounding the invariance. And so the first thing that you do in order to control these walls is that you bound the rank of the walls that can happen. And in case the rank is higher, then, you know, you can bound the invariance. So now you have a good bound as to what are the possibilities. So you either have a rank 1 wall, or, you know, you have some bounds on what rank 2 walls can appear and things like this, right? And then, you know, you go through the list and you can enumerate these things. So, you know, you can actually fairly algorithmically do some of these things. All right. And then you see that there is a one-to-one correspondence, at least in these examples. Like, you know, I had 6, you know, 6 walls here, and I have 6 walls here, and things like this. It turns out that this is actually a general theorem. So this was conjectured by, you know, this was conjectured by in joint work with Arcara, Bertram, and Jack Huizinga. And then, you know, since then has been proven, you know, by Bayer, McCree, Chunyi, Lian, Shale, and Zhao. So, but basically what it says is that there is a one-to-one correspondence between, you know, the walls in the Mori, the walls in the Mori chamber decomposition and the Bridgeland walls. So this is, we're talking about P2 here, right? And, you know, the correspondence is fairly concrete. You know, whenever you have mu h minus b over 2 is, you know, So let's see, how does that work? Whenever like, you know, you have a ray spanned by mu h minus b over 2, then I believe the center of the wall is mu minus 3/2, or minus mu plus 3/2, something like this. Okay, so there's like a very explicit, very simple correspondence between them. And then the way you should think about it is that what ends up being in the stable base locus in the Mori chamber decomposition corresponds to what gets destabilized at that wall. So, you know, it's a fairly concrete, correspondence. And then, you know, you can use this either way. I mean, you can use it to figure out what's happening in the birational geometry by thinking about Bridgeland stability conditions. And then you can understand, like, you know, Bridgeland stability conditions by, you know, knowing what happens in the birational geometry side of things. Okay. And then the key point, like, you know, so in terms of Bridgeland stability, you can also explain what the effective cone is, and you know, you're already seeing this to a certain extent, that the last walls that I've been giving you have been given by O of -2 here, O of -1 here, you know, the tangent bundle of P2 twisted by -4 here. So, you know, the theorem that we had last time, that we can understand the effective cone corresponds in this picture, that the last wall, the collapsing wall, the smallest wall, the collapsing wall is always given by an exceptional bundle. And it's, you know, the exceptional bundle that's determined by what I described by, you know, the procedure I described last time by, you know, that sort of, you know, we looked at the classification of stable bundles, and then we looked at the, you know, the orthogonal parabola, and that it met the Dresel-Potier curve in one peak, and then there was a controlling exceptional bundle. Okay, so this is sort of two different ways of looking at the picture. And then, you know, in my experience, if you want to understand the cohomology of sheaves, or you want to understand the birational geometry, the most useful thing is the interaction between these two. There are some things that are easier to do in the Bridgeland picture, and there are some things that are easier to do in the Mori picture. And then actually going back and forth, guessing what the answer should be, usually gives you like a lot of power. So I think I'll just stop here. So this is, you know, a relatively brief introduction to the subject. Hopefully you can, you know, look at the papers, and this is a very active area. A lot of people are working on this. So, you know, you can look at what's going on. Hopefully it will give you some picture to sort of be in order to be able to follow what's going on in the literature.
All right, thank you very much for the great lectures. So any questions? Justin? Okay.
Yeah, actually, so, oh, there's a question.
Yeah, okay, yeah, just go ahead.
Given by the discriminant. What does that mean? I'm not sure I understand the question. What do you mean by is it always given by the discriminant?
Is the smallest wall always given by the discriminant? if you put the equation of the discriminant equal to 0, it gives the equation of the wall.
I don't think so. I mean, it's like you can't just set the discriminant equal to 0 because there might not be a bundle with discriminant equal to 0. Like, so like, okay, so let me just, so, if you have a stable bundle, right, then Bogomolov's inequality tells you that the discriminant has to be greater than or equal to 0. But this is very rarely a sharp inequality. Like, it is sharp in the sense that for line bundles, you really have equality 0, but like the equality, but, already we classified, stable vector bundles. Yes, there are these points, but, like, really, if you have a Chern class that's not an integer, right, the discriminant of a stable bundle already starts like by something above a half. Yes, you have this line bundle, so in that sense, this inequality is sharp, but typically, if you want to get an equality depending on the first Chern class, then it's not sharp. So, you do not have a vector bundle with discriminant 0 typically. Like the Bogomolov inequality is typically very not sharp. And it is a big question as to what are the sharp Bogomolov inequalities. And then you're right that, like, the smallest wall is very closely tied to the, possible discriminant of vector bundles on possible discriminants of stable vector bundles on the surface. But typically it's not just given by equal to 0. That comes to the question of we don't understand really when the moduli spaces are non-empty. I don't know, does that answer the question? Maybe.
Could I ask a question about the n equal 3 picture?
Yeah, let's find the n equals 3 picture. Yeah.
So in this case, when you cross the largest wall, the destabilized locus is a divisor.
Yeah.
So when you cross that, that's just a divisorial contraction.
That's just the divisorial contraction, yes.
So if you look at the short exact sequence for objects there, then you're switching the kernel and the co-kernel.
So
is that right? But when they're when you switch them, is that saying there's a unique extension when you switch the order?
Probably. We could. It probably says that, but I haven't checked that, so let me not definitively say. But
and then when you hit the smallest wall, then everything is in a destabilizing locus.
That's right. Everything is in.
And when you switch the order, there are no extensions, so you get the empty set.
Right.
So with the n equals 7 picture, is it the same sort of behavior when you, as you cross each wall? Is the destabilizing locus replaced by something of bigger codimension?
Is it replaced by something with bigger codimension? Not in general, I don't think. Yeah, not always.
But it should be true though that if you, let's see, if after you pass the wall, if there are no extensions in the opposite order, that means you would then have the empty set. Or at least, sorry, at least that, I mean, you can't replace a destabilized locus by the empty set, unless that destabilized locus was the entire moduli space. So if you hit a wall and your destabilized locus is a proper subset, then when you cross the wall, it has to be replaced by something. So there has to be some extensions.
Right, but you have to also be a little bit careful that, like, you know, somehow, like, you can also like you know, as you keep doing this more and more, right? Like the kinds of things that you have to worry about is that some things become stable for a while and then they disappear again. Right? I mean, like, it's not, I mean, like, you know, so like, you know, you can start with an ideal sheaf and replace it with something, right? But like, there is no guarantee that you don't replace that again with something else. Right? I mean, so you have to be like, I'm being a little bit, you know, glib about these things and just sort of trying to paint a picture, but that's not, yeah, you know, you do have to worry a little bit that, like, you know, as you have these walls, right? Like, you have to worry that about things like, you know, something is not stable. At some point you have a stable object and it disappears again, like, right? So like, it's not necessarily true that, you know, once you're stable at some point that you persist all the way to the top and things like this. Right. So you need to worry a little bit about these kinds of things.
But you couldn't, you couldn't replace a destabilizing, you couldn't replace a locus by an empty set unless the locus was the entire moduli space. Otherwise you would have like a quasi-projective moduli space after you cross the wall.
Again, I mean, you know, let's, like, if you're talking about P2, like, you know, you could have like many components to some of these things and some components can disappear.
Oh, yeah, right, okay.
Like, but you know, in the case of P2, these things turn out to be irreducible. So then that's okay. But like, you need to be a little bit careful about some of those kinds of things as well.
I've been mainly thinking about the K3 case.
The K3.
In the K3 case, is it? Do you always get a flop?
So in the K3 case, like, you know, this collapsed, even past the collapsing wall, things can still, like, there are still moduli spaces. It's possible that you destabilize every ideal sheaf. But the moduli space is not empty.
So I mean, the thing is,
walls are called whatever, strictly semi-stable walls, and there is a description of those things by Bayer and McCree. Like, you know, they correspond to very special, you know, basically the typical example of such a thing is that, you know, you have a spherical object. It's destabilizing it, so that you destabilize all the sheaves, but then, you know, you have these complexes below it. Right. So
in the K3 case, so the X groups, I mean, by seriality, when you switch your order, you're getting the same X1 is still the same dimension, right? So that kind of suggests that you always get a flop, but it's not quite like that, or?
You always get a flop.
Well, if the destabilized locus is a proper subset, if it has positive codimension, then it looks like you would always get a flop of some sort.
Yeah, it's possible. Yeah, I mean, in the K3 case, there are some other things that can happen. So for instance, I think there are examples where actually the moduli is not changing, but the universal family is changing and things like that.
Oh, yeah.
So there are some other.
That's your totally semi-stable wall.
Yeah, there's some other interesting things happening. Yeah.
But if everything is in the destabilized locus, that means that everything's given by an extension like this.
I mean, what can happen is
does that mean
all
that's
sheaves get destabilized at some point, but then you have these complexes that are stable on the other side. That can happen in the K3 case.
see if something's in this destabilizing locus and it's given by an extension like this.
Yeah.
So you have some class in projectivization of x1.
Mm-hmm.
So if everything's in that, doesn't it mean you have some sort of that the thing is rationally connected in some way, or not quite?
What's rationally connected?
Well, somehow it's covered by.
I mean, these moduli spaces
P1s, isn't it?
P2 are always unirational, I think.
Right, but in the K3 cases, it couldn't be.
Oh, no, in the K3 case, it couldn't be, but like, right. Yeah,
I'm just saying, like, if you have a sheaf that's an extension, then it's given by an extension class. So you have the projectivization of x1 is parameterizing some family of sheaves. And if everything is given by an extension like that, then it's covered by projective spaces.
Mm-hmm.
But in the K3 case, that can't be happening because the moduli space can't be uni-ruled.
Right.
So that's, yeah, I'm not sure why. Well, I guess I need to go back and look at McCree's paper. I'm sure they address this somewhere.
Right.
Okay, thanks very much.
All right.
All right, thank you very much, Izzet, for great lectures. So this is the final talk. Tomorrow there might be a session in 10:30. I'm gonna email about it if it happens for Özgür. Thank you very much for attending the 5th graduate summer school, and follow us for new schools coming. Thank you very much.
All right, thanks, Mustafa, for organizing everything.
Thank you very much. See you again.
All right, bye.